Welcome to the lecture Digital 3D Documentations in Archaeology. In this lecture part, we want to talk about recording strategies for aerial documentation campaigns. Here we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. Every pilot must be able to fly a documentation area independently by hand without using automated flight planning for it. In doing so, he must internalize the structure to be recorded and systematically select the appropriate flight patterns and recording strategies that are necessary and successful for the subsequent 3D reconstruction process. Often there is only a short time window for such an acquisition, so small mistakes and carelessness may be severely punished later. With automated flight planning, large contiguous areas can be covered, but for a successful 3D reconstruction, often further acquisition strategies are necessary. Let's start first with flight preparation, protection, and team briefing. We had already familiarized ourselves with the rules for dealing with multicopters. The first point mentioned was this: the flight area must be secured, and all participants involved must be informed about the planned flight. Now let's discuss that in more detail. Again, the following important point has been listed in the rules for safe handling of multicopters. The flight area is secured and all parties involved are informed about the planned flight. This rule includes very different things depending on the documentation location. The responsibility lies with the pilot. In a well-coordinated flight team, the tasks can be distributed and guided by checklists. This saves time, minimizes the risk, and increases the chances of success of the flight campaign. The necessary steps can be clearly described by the following three parts: preparation of the multicopter and the camera, securing and preparing the documentation site, and a detailed team meeting. Flight preparations include many important points regarding the hardware used, which should be worked through in a checklist before each flight. Are the propellers neatly mounted and the motors intact? Are all extensions of the multicopter securely attached and ready for use? Are the batteries for multicopter and controller fully charged, and thus the multicopter ready for use? Is the camera lens cleaned and the camera mount intact? Are the memory cards empty and inserted? Is the camera recording mode set as planned? Are the batteries for the camera charged? Is a log for the recording flights ready? It would be a great waste if a nearly full memory card at the end of a flight was responsible for the fact that an acquisition strategy could not be carried out completely and had to be repeated. Legal issues must of course be clarified, and the owner's written consent must be obtained before an aerial survey can be carried out. To protect the documentation site can include several points, and these can be very different. If necessary, the site of the flight must be protected with barrier tapes or other measures. Placement and measurement of the control points, survey points, or ground control points in the terrain. All team members wear clearly visible safety vests, making it clear to all non-participants that this is a special situation and that care is required. Preparations for the documentation site include deciding in advance whether georeferencing of the structure or terrain model to be created can be automated or whether ground control points will be placed in the terrain. Before the documentation flight can really begin, each participant must know what role he or she will play in the documentation and how the documentation is planned. The roles and tasks include: pilot. Who is flying the multicopter? Is there a co-pilot who takes over communication with the other parties involved or keeps an eye on the multicopter? Who is responsible for securing the documentation site? How does the communication take place during the flight? In case of several flights, who takes care of the provision of the batteries and memory cards or monitors, the cooling batteries and recharges them if necessary? Who takes over the task of the logger? This is very important for many reasons. First, multiple eyes can monitor the flight from different perspectives and provide useful guidance during or after the flight. On the other hand, unexpected events such as the appearance of uninvolved persons, can be better intercepted by the team. The rule here is, the pilot must not be disturbed during the flight, and communication with the other participants is exclusively via the co-pilot. Clear agreements and established procedures not only speed up documentation recording, they also ensure safety. Let's take a look at manual recording strategies in an ideal case. Normally, a camera is mounted below a multicopter so that we can only record objects and structures from above and the side with this camera. For the further classification of the acquisition strategies, we distinguish acquisition flights in which either a vertical, we call it orthogonal, or an angled, we call it oriented, camera position is present during the complete acquisition. An angled camera has the advantage to see objects and structures from the side. However, since we can only see one side in a flight direction, in most situations we have to perform more flights than with a vertically mounted camera. If the goal is a complete image of a documentation site, the structural properties determine the choice of acquisition strategy. The target can be an orthophoto, a 2.5D model, or a 3D model. For the first two cases, orthographic recording strategies are often sufficient. If the documentation site has a higher degree of complexity, we think of cube-like, simple buildings, then we need already oriented recording strategies. Structures that have overhangs, for example, where an additional camera has to be used, become challenging. Here it is also crucial to bring the image sets together at the end and to think of the necessary overlaps. The decisive criterion for the successful determination of a 3D position from a set of images is the overlapping of the image contents. Only when we have seen an image element in context to other image elements from different perspectives, we can determine 3D points from it. If we are traveling in a direction of flight and systematically taking images, we can independently control the overlap in one direction. Now, to guarantee an overlap in the second direction as well, a parallel flight must have the corresponding image overlap. If we take an orthogonal flight as an example, then a parallel offset return flight can already provide the necessary overlap. In this way, rectangular areas can be flown and recorded systematically. We call this recording strategy Orthographic-Grid-Flight, and it represents the simplest recording strategy. In the orthogonal grid flight, parallel paths are flown back and forth. Although area B was imaged in the image acquisitions, the smaller area A is delivered at the end of the reconstruction process due to the lack of overlap. The pilot in green and the co-pilot in yellow walk together along the paths of flight. At the end of the path, another team member can ideally take over the monitoring of the recordings and the documentation area. There may be additional eyes monitoring the process, depending on the complexity and size of the documentation site. To increase the overlap of the different flight paths and thus improve the reconstruction, another 90-degree offset flight can be performed. We call this imaging strategy Orthographic-Double-Grid-Flight. The double coverage of the imaging area is preferable, especially in difficult imaging situations, where, for example, bad single images or slightly offset fly paths can occur due to wind. However, the time required doubles during recording and often quadratically increases the computational complexity. The two recording strategies, Orthographic-Grid-Flight and Orthographic-Double-Grid-Flight, are suitable for relatively flat terrain structures without large differences in elevation, with the goal of creating orthophotos or 2.5D models. Here we see a suitable situation of a large flat area for the Orthographic-Grid-Flight, taken in 2013 during road construction on the B95 near Leipzig, with the Saxony State Office for Archaeology. Flying a flat documentation site is by far the easiest. With an angled camera position, it is clear that only one side of the objects and structures may have been seen correctly, and we may need to record all four sides. To develop a shooting strategy from this idea, for a shooting flight of the front sides, we can consider the parallel return flight the same as a shooting flight of the backside. Important here is the halving of the distance between the flight paths compared to the grid flights from section, because the overlap is analogous to the orthographic grid flight only for one direction. This means that we can take two sides with one flight, but we need twice the flight distance and therefore twice the flight time. If we want to complete the side views, we must also perform another oriented grid flight rotated by 90 degrees. However, this again doubles the effort required for the recording. Compared to the orthographic grid flight, we have 4 times the number of individual images and therefore also need 4 times the time for recording. For the recording planning, not only the time required for the flights is now interesting, but possibly also the resulting time required for the subsequent 3D reconstruction, which we should not disregard here. In this table, we start in the first row with the orthographic grid flight, where n single images are taken. The time required for this is in linear proportion to the number of images. This means that twice the time is required for twice the number of images. For example, if we take 1,000 images in 15 minutes, for an orthographic grid flight with a pre-planned overlap in both directions, and need 1 hour to calculate the 3D model, then a double grid flight would take twice the time with 30 minutes for the flights, but due to the 2,000 images taken, it would also take a calculation time instead of twice the time, even possibly 10 times the time. Thus, there is a linear relationship between the number of images captured and the time complexity for capturing, and a quadratic relationship between the number of images captured and the processing time. The two recording strategies, oriented grid flight and oriented double grid flight, are suitable for more complex terrain structures with the aim of creating 3D models. Here, for example, excavation sections or elevated structures can be well recorded and reconstructed. This example shows a typical excavation situation in the Galleriestrasse in Dresden. The excavation of the Saxony State Office for Archaeology was accompanied by several aerial campaigns in 2013 to 2014. The excavation area represents a recess. Here, in order to capture just the inside sidewalls, we must choose a capture strategy that involves an angled camera position. In this case, an oriented double grid flight was selected. The difficulty increases due to the increased structural complexity, but also due to the location within the city. A very important recording strategy is the circular flight around a structure with the camera direction towards the center at almost the same distance. This flight variation is very challenging and requires a high degree of concentration and practice. At different flight altitudes and possibly with different camera orientations, several circular flights can capture the object or structure. With the camera pointing inward, we turn in a circle around the freestanding object. Since the flight maneuver is very demanding, the pilot does not move from the spot. The opposite side must be secured. In circle flight, the pilot flies around the freestanding object with the same camera orientation and constant altitude. Various shots with different heights, or the combination with the helix flight, provide the necessary video data at the end. Here, for example, excavation sections or elevated structures can be well recorded and reconstructed. Elevated freestanding structures often require an elaborate imaging strategy. In this case, we see a Huastec temple complex in Tamtoc in Mexico, some of which has dimensions of over 100 meters. The reconstruction of this and other sites and the surrounding area was carried out in 2013 in cooperation with the Instituto Nacional de Antropología e Historia, INA, and the Universidad Autónoma de San Luis Potosí, UASLP. Several helical flights in combination with an oriented double grid flight were chosen for the handheld acquisition with a DJI Phantom 1. In the 3D reconstruction process, the internal camera parameters are estimated in addition to the external ones. If we use a camera with fixed focal length unchanged, the determination of the camera parameters is especially accurate. Also, different shooting strategies with many crossing points between the trajectories can influence the parameters very positively, A particularly effective recording strategy, which not only investigated the crossing points but also brings together different flight altitudes, was investigated and presented by James and Robson in 2014. First, an orthogonal grid flight is recorded at a constant flight altitude. Then an opposite flight is performed on the same trajectories, rotated by 20 degrees and about 5% higher. These have been theoretical recording strategies so far, but what do the recording strategies look like in reality? In the last slides, different recording strategies were presented in terms of ideal properties of documentation sites. In reality, however, documentation sites have much more complex structures and characteristics, which requires a combination of different recording strategies. Here we see a complex coastal situation recorded during a documentation campaign in Punta di Zambrone in Italy in April 2014. The challenge was to place a sufficient number of markers in a clearly visible position and to plan and carry out the flight for parallel recordings. Even without GPS and live video data, complex structures and large terrain areas can be successfully recorded and documented in a team. Certainly the effort is many times higher, but with the knowledge and experience in the background, 3D reconstructions can be carried out even with technical difficulties. Here, of course, it helps if we can see very quickly results of 3D reconstructions. We see again the example from Italy in Zambrone. Here, for example, we can quickly see in the ortho image if the markers are well visible. We see here a section of the ortho image, and at the bottom in the center one of the placed and measured yellow markers. To ensure that a documentation flight runs safely and as smoothly as possible, it is essential to work through checklists and keep logs. This means that each recording can be traced back to a specific pilot at any time after a flight. Not to mention the fact that thousands of images can be created in a very short time, and that the subsequent processing requires well-managed protocols, especially in the case of long documentation campaigns. Calmness and care are required when taking minutes. Things that have been noted incorrectly or carelessly in the log can often only be reconstructed with great difficulty, if at all. For example, as shown in this example, the batteries used are also noted in the log. Bottom right, we see the documentation campaign in Mongolia 2018, in which 204 individual flights were carried out at the end by more than 50 square kilometers. Whether a protocol is kept digitally or on paper is not important at first. There are various apps in which the log can be kept. A protocol can also be adapted to a documentation campaign as needed. However, the following contents are important and relevant for each implementation: date, place, copter, pilot, start and end, time of the flight, LiPo ID and remaining capacity, wind speed and special remarks. If several devices are used in parallel, the copter can be noted in the log, or a separate log is kept for each device. The correct start and end times, as well as a synchronization of the various system clocks with respect to the recording location carried out at the beginning of the campaign, facilitate the assignment of the image recordings to the flights and thus to the missions and flight areas afterwards. With the LiPo ID, we have the number of charge cycles in view, and with the remaining capacity, the team is sensitized to not push the battery to the limit. Here we can also see good and safe flight planning designed for safety. The maximum flight time for a Phantom 4 Pro is stated to be over 20 minutes. For the Mongolia campaign, it was taken into account that the flight site is located about 1,500 meters above sea level, and that temperatures between 5 and 15 degrees can be expected. The missions were therefore planned in such a way that a flight could be completed in less than 12 minutes. Under special features, things can be entered that are directly related to the recording. If a flight had to be interrupted and repeated, or there was a weather change, then special attention should be paid to the recorded data. We distinguish here between the direct flight post-processing phase, which takes place after a multicopter has landed, and the post-processing of a complete documentation day with several recording flights. After the multicopter has set down for a landing and the device has been switched off, the battery is changed in any case. It must also be clarified whether the memory card used with the recordings is also changed for the purpose of data backup or remains in the copter. Before flights near water or in other unclear situations that pose a risk to the data recorded so far, the memory cards should be backed up by changing them in any case. Important in the post-flight phase is also the completion of the log. Here it should also be clarified whether the pilot needs a break, and the task distribution is changed if necessary. Typically, several recording days are required for the larger flights. Here, it is especially important to back up data after a successful recording day and prepare the equipment for the next day. After a documentation day, the double backup of the recorded data and thus the correct assignment of the recorded images or videos to the missions is an important and decisive factor. Here we see the post-processing phase of a documentation day with more than 30 flights in the yurt. The captured images are assigned to the planned missions with the help of the logs, sifted and then double backed up. Here we must leave nothing to chance and minimize the risk of data loss. Reviewing and saving data multiple times after a documentation day is an important part of documentation work, and its importance should not be underestimated. During the data backup, the data can be checked for completeness and quality. What good are the best flight maneuvers in the best recording weather on an important recording day, if at the end of a documentation campaign it is discovered that a faulty hard disk or a defective memory card has made all the work for nothing? In parallel with the data backup, the equipment can be checked and the batteries charged. This phase often takes a long time and should also be carried out carefully. Now let's move on to exercise scenarios that can be performed as a team. Safe and practiced handling of the working equipment is very important for a successful documentation campaign, especially the flight maneuvers already presented and typical hand movements that are necessary in the preparation, recording, and post-processing phases should be practiced regularly. Experienced and trained pilots can perform the exercise scenarios presented here with beginners and thus slowly prepare them for the safe handling of multicopters. For all suggested exercise scenarios, a workflow is provided to be performed each time. The sequence of steps is very important, which can and should be explained by the experienced pilot. The suggested flight scenarios should be performed in the order given, with breaks in between. Regular handling of the working equipment, or at least before a campaign to refresh and reactivate, the knowledge should be part of the standard repertoire of an experienced pilot. A few practice scenarios with different levels of difficulty are also presented. The following exercise scenarios are to be performed only under professional supervision and in a secured location. The following exercise scenarios are embedded in the presented workflow and are only useful in the suggested order. After each exercise scenario, problems and uncertainties should be discussed. If necessary, a scenario is repeated until there are no more difficulties. After listening carefully to this lecture, answering the following comprehension question should help you to summarize the most important statements again on your own. The practical part is about getting to know the COLMAP software and processing a known data set. Here are the important steps in COLMAP once again.